Hi, my name's Louie Petrone. I've worked with Leenhouts, Patrick Rojek, and Alex Kuhn on this project, and we are Pure Chemicals LLC. We were contracted by Line Chemicals to find alternative methods to make sorbitol cost effective and produce more products. This is the reason is because we are losing subsidies of sorbitol to gasoline. But we were given conditions that the products that we produce have to be a purity of 99.5% by mass. The plant must be built by 2019, and operation hours are 8,400 per year. Our location that we've chosen is Houston, Texas, and our flow rate that we've got that was handed to us was 72,000 pounds per hour of process.
Hello, my name is Leenhouts. I'm going to talk to you about the process we're using to recover the value from our sorbitol that's being lost because of the lost subsidies. We used the beginning for our reaction is based around our reactor, where we're using a ruthenium-based catalyst to cause a reaction that produces additional products. We got this catalyst and reaction from a patent that we've been analyzing. In order to do the reaction, we use raw materials of sorbitol, sodium hydroxide, hydrogen, and water in order to make a solution so that it can all mix and react. We maintain this reaction at high temperatures and pressures so that the reaction progresses in the correct order and maintains the selectivity towards the products we want. From the reactor, we're recovering a large amount of mass as the products, and from the product stream in our base case, we're recovering 74% by weight percent of the products. In order to make sure this process works effectively and cheaply, we have to purify our product streams. This starts off with our ion exchange resins. In order to prevent any contaminants of sodium hydroxide or salts from municipal water, we need ion exchange beds to remove the ions. The cation beds and anion beds at the very beginning of the process clean municipal water to create pure water that won't have any deposits build up in the reaction as it progresses. We also use a sodium hydroxide removal ion exchange bed in order to remove the sodium hydroxide after the reactor, because the sodium hydroxide does not react but is just used for reaction environment. It stays in the product stream and could cause corrosive issues down the line. So we use hydrosulfuric acid in order to remove the sodium hydroxide. This minimizes capital costs as it reduces the number of pieces of equipment that need to be made out of stainless steel. After we purify the contaminants out of the product stream, we separate it through distillation. We had 4 main distillation columns in our base case. Our first column, T100, is focused around removing water and alcohol. This minimizes the mass flow through the entire process so we can keep our utility loads down. After T100, we move on to T101, where we remove all the heavy contaminants, which are the heavy wastes, which have lower volatilities than our products. Then we move on to T103, where we remove the ethylene glycol product. We purify this to the hard spec of 99.5 weight percent in order for us to be able to sell it. Here we remove the ethylene glycol because the final column focuses on the separation of propylene glycol and 2,3-butanediol waste. That separation is very difficult. As you can see from the column efficiency graphs we have, the TXY diagram is very close, so that takes a very difficult and many-stage distillation column. So we minimize the utilities around that. And we use knee of the curve analysis method to be able to minimize the reflux ratio to column tray to make sure we had the best possible columns, not only for T104, but for all of our columns. After distillation, we had to dispose of our wastes. Out of the T100 column, we had a lot of wastewater. Originally, it comes out at a mass concentration of, or a contaminant concentration of 7,100 parts per million hydrocarbons. This exceeds the 5,000 parts per million hard spec we have to hit to be able to dispose of it through normal means. In order to hit the spec, we dilute the water with an additional 50,000 pounds per hour of municipal water. This is more cost effective than an additional distillation column because it's likely that the distillation column to bring it up to that mass purity would be similar to the T100 column, which would have a greater capital cost than the $5 million required for the utilities upgrade and the $3 million utilities cost per year that's required to run the column. We spend less money on the waste or water disposal. From all of our hydrocarbon wastes, we were actually able to mix them and surpass a 10,000 BTUs per pound threshold to allow it to be burned for fuel credit. In addition to the hydrogen waste stream, we were also able to burn this, making it so that we weren't actually disposing of any waste besides our wastewater. And we were able to get about $6.2 million per year back for fuel credit costs. The hydrogen waste we were not able to, we had to burn it because the recycle was not feasible because of issues with gas membrane, poisoning, separator not being feasible with liquids getting caught up in the vapor, and issues with a series of compressors and heat exchangers being far too expensive to make our hydrogen recycle cost effective. Here we have our BFD outlining the basic process layout we have, starting with our feeds, going through the heat exchangers, into the reactor, getting pumped into our ion exchange, and finally into the distillation columns.
My name is Patrick Rojek, and I will briefly summarize the determined capital costs for the process. So in determining the capital cost for the process equipment itself, considerations were made based on dimension size and materials of construction. Materials in construction came into play, especially with downstream equipment initially at the beginning of the purification process, due to corrosive components involved in that are products of the reaction, which were lactic acid and sodium hydroxide in particular. Starting with the reactor was priced at a price of $37.1 million. The area is comprised of a compressor, pumps, and the 3 reactors themselves. The main cost associated with the reactor area was the compressor, which requires a huge pressure change to bring the stream pressure to the required specifications per the patent. Next was the ion exchange area, which is for 2 ion exchange beds. One will work at a time, and the other is used for times for changeover. This came out to $4.1 million. Next was the columns themselves. T100, which was comprised of the column, reflux drum, and the associated pumps, as well as the heat exchangers, which is for the distillate and the reboiler, came out to $10.7 million. The next column, T101, came out to $6.5 million. Next, T103 came out to $6.2, and lastly, T104 was $6.1 million. This for a total of IBL costs of $70.8 million. Next, to determine prices which were considered OBL, such things as utility and site development, using past projects that were completed by Knit-Lion, we scaled the costs and came up to a total OBL cost of $72.1 million. In total, the total plant costs, which was determined, was $236.4 million. An attempt to reduce some of the capital costs involved with the project, process integration was attempted using some streams at high temperatures to act as a heating fluid for cooling elements in the process. However, in the end, this ultimately did not produce enough duty to produce any worthwhile savings. The final attempt, I guess, and the best use of the heat exchangers was to split up in using the medium process heat steam first, and then going higher to HPS. Ultimately, after considering all the costs associated with the process, we found out that the cost of the raw feed required to conduct the process compared to the pound of product produced came out at 52.34 cents for the sorbitol feed. Next was the hydrogen feed required, which was 14.68 cents. Total required, which was including the sodium hydroxide and any other reactants required, was 70.18 cents per pound of product produced. Next was the licensing fee. So for the propylene glycol licensing fee, another 35 cents is required per pound of product produced. Then there are the utilities. Utilities were a huge cost in this process, and per pound product was 21.25 cents. Then there's associated fixed costs with the process, which per pound product was 4.06 cents. Total cash costs per product produced came out to 95.96 cents required with our current process. However, we can only sell the sorbitol at 66.65 cents. 69, roughly 70 cents. So ultimately, we're operating this process at a loss.
Hi, I'm Alex Kuhn, and I was in charge of the sensitivity studies. We knew since we were running at quite a deficit with our product that we needed to do some sensitivity studies to see if the future could have any possible profitable years. So the first sensitivity study we really looked into was just the raw material costs and how they've changed over the years. We noticed that hydrogen is quite a volatile chemical as far as the price goes, while NaOH and sorbitol are both pretty stable. This led us to believe that while the NaOH and sorbitol take up most of the cost, and we can predict that that'll be about pretty level, the hydrogen cost could either skyrocket or drop, and that could still significantly affect the cost of our reactants. And our base case for the last 5 years averaged, we got a product net worth of 1.2 million without including the utility costs. And that was the average of 4 good years in 2015, which was a down year. In 2015 alone, our products were worth 15 million less than our reactants. The future from this is pretty difficult to predict, but looking at the other trends, considering the raw products with the raw materials with the products, I wanted to look into seeing how they follow each other in trends. And looking into that, I noticed that all of the chemicals seem to follow similar trends. When one chemical rises in price, it seems the rest do. So it's pretty hard to predict that hydrogen's price could significantly drop while the other prices could remain stable, meaning that it's pretty likely that we're not going to get a very favorable year in our products versus reactants. The next study we did was our product values over time, and we looked over the stability of the last 5 years. And the base case average product value of just selling the propylene and ethylene glycol ended up being roughly 70 cents per pound. From our economic analysis, to reach our ATROR of 15%, our average product value had to be $1.10 per pound, which by looking at the chart, it's impossible. The average prices could never get that high, considering that none of our prices actually ever reach that high. So we had to look in alternative processes to see if anything else is good. Another thing we noticed on it was that the stability of the products is they're not quite stable, they're pretty volatile themselves, which also makes it pretty hard to predict the future, whether or not we could actually make money off the process. Then we did a sensitivity study of the product values with the price of oil, because oil's price has been extremely volatile in the past few years. And what we really found was that both propylene and ethylene glycol mirror oil's price almost exactly. So when oil spikes and oil drops, so do their prices. Our base case purely sells propylene and ethylene glycol. So if oil drops, our products significantly drop, while some of the other chemicals are not affected, meaning our reactants could actually end up staying stable while our products significantly drop in price. To mitigate the oil volatility risk, we looked into selling the 2 chemicals that were not affected by this price, which were lactic acid and 1,4-butanediol. Then we looked at natural gas price on the effect of our utility costs. And right now, natural gas is at a pretty low price, and our utility costs are still extremely high. Even if natural gas is at $2.5 per MMBTU, the utility cost is still $49.5 million, meaning we're running in a significantly negative zone. Since we're already running the tight margin, it's pretty hard to possibly imagine us making a profit And if natural gas rises in price, there's no way we could ever make a profit.
We've also studied alternative cases for our project, such as producing side products of lactic acid and 1,4-butanediol, which increases the recovery of the product to 93%. We've also considered wet water recycle, but we found that there's more water leaving the reactor than required. But on the plus side, there's no water purchase and there's minimal water disposal costs. We've also dug into hydrogen recycle. We originally had this in the design, but we decided that it wasn't feasible with a gas membrane. We're questioning if it might be feasible with an absorber, and there's a potential $30 million per year lower raw material cost. The economic evaluation of the alternative case study is such as this. The summary, we found that the capacity runs at increases to 450 million pounds per year, and the capital cost increases to $243 million per year. The raw material costs in total decreased to 59.29 cents per pound of product from all. The licensing fee, we found that the propylene glycol decreased to 0.29 cents per pound. The utilities total, we found that it decreased to 17.99 cents per pound. The fixed cost in total, we found that it decreased to 3.44 cents per pound. And our alternative case selling lactic acid in 1,4-butanediol increased to 71.7 cents per pound, but we also still have a negative deficit of 9.31 cents per pound. Our final recommendations are this. With the current trends observed in the sensitivity studies and economic analysis, it is not recommended that the plant be built in this current market. While some of the alternative cases could cut some utility costs and make the process profitable, more studies need to be performed. It is, in our professional opinion, the volatility of the ethylene and the propylene glycol market make this incredibly risky endeavor. Even selling lactic acid and 1,4-butanediol cannot make up for the potential losses incurred from the price drops of ethylene and propylene glycol. Unless the price of hydrogen and sorbitol significantly drop, it is not worth the capital investment.